All right. Here we are again. So I hope that you were able to get your assignments done. So anyway, in the meantime, we're going to start up with 6 again. We started it. We didn't quite finish it. In fact, we didn't get all that far into it. So what I'd like to do right now is quickly review what chapter 6 is all about. Oh, get that open. Yep. Now, luckily for us today, is in this chapter, for the first time, we're going to see some seriously important techniques that we can use on our calculators to help us with a lot of these complicated situations. And so I hope you have your calculators right there. You're definitely going to need them. All right, so let's get cracking here. Okay. Today's the 14th. All right, so just quickly, we introduced the concept of the random variable and the probability distribution, which we'll be using throughout the rest of the course. In fact, many of these chapters are dedicated entirely to different types of probability distributions. So we started out by defining a random variable as simply a function that assigns numerical values to the outcomes of a random experiment. Because in most cases, it's more convenient to deal with numbers than with letters or colors or flavors, whatever the case may be. In our example with the dice rolling experiment, we were using EE, EO, et cetera, So it's probably easier to think of those as numbers rather than letters. So the random variable is taking all the different possible outcomes of the experiment and basically converting them into numbers. That makes our job a lot easier to calculate probabilities. It also makes it easier to define formulas to calculate these probabilities. Okay, doing it from a table is fine as far as it goes, but most of the time that's very inconvenient. It's much easier to have a formula. All right, so let's just jump ahead a little bit here. With our die rolling experiment, we had a sample space that consists of EE, EO, OE, and OO. And remember, we were only interested in the evens or odds of each roll, not the actual number. And we saw that there's only 4 possibilities, each of which is equally likely. So what we did here is we define X to be the number of evens that turn up when we conduct this experiment. And you can see the range of possibilities is from 0 to 2. So EE gets 2 because there's 2 even numbers. EO and OE both get a 1 because these are both even numbers, or they have a single even number, and then OO 0 because there are no even numbers. Okay, so what we also determined is that because each of these outcomes is equally likely, each one has a probability of 1/4. So we can now associate probabilities with these numbers or these values that we've associated with X. For example, the probability that we get a 0, X equals 0, is 1/4 because this is the equivalent of getting OO. Okay, so in other words, X equals 0 means the same thing as getting 2 odds. This one up here. 1 is a little trickier because there's 2 ways we can get a 1, either from getting EO or OE. Since each one has a probability of 1/4, the total probability that X equals 1 is 1/2. And then for 2, of course, that's the same thing as getting EE, and that probability is 1/4. Okay, so we can bring these all together and then put them in a nice little table. And so we don't really need this first column for our probability distribution. But the probability distribution is actually columns 2 and 3. It's a list of all the different possible values of X, followed by their probabilities. That is an example of a simple probability distribution. And the table can have as many events as we want. X could have more values than just 3, and if it does, we just have a bigger table. What we do note here, though, is that number 1, usually probability distributions are expressed as a formula, just because it's easier to deal with it that way, especially when there's a large number of X's. And number 2, in order for any probability distribution to be valid, it has to have two key properties, which are taken from the axioms of probability. Number one, each individual probability has to be non-negative. Okay, it can be 0, but it can't be negative, and then they all have to add up to 1. Okay, so that means, in other words, each of these individual probabilities is bounded between 0 and 1. And in addition, the sum has to be exactly 1. So we can't have any negatives in here, but we also can't have any that are above 1 either, because the total has to be 1. And without any negatives, that implies that each one is between 0 and 1. If the probability distribution doesn't have these properties, then it is not a valid distribution, and we can't actually derive any results from it. Or at least if we do, they won't be correct, that's for sure. So I put together here a couple of quick examples of invalid distributions. The first one is not valid because the sum is not 1. It's only 0.9. We missed something. So that can't work. The one on the right, they add up to 1, but there's a negative in there. So if we tried to use these distributions to obtain results, we would get an incorrect answer, for sure. Now, we also define two different types of random variables. They can either be, well, for the most part, they can either be discrete or continuous. It's theoretically possible to have other types, but these are by far the majority of the random variables that you're likely to encounter. Discrete simply means there's only a finite number of possibilities. Like here, X only has 3 possibilities, 1, 2, and 3. That makes it discrete, okay? In order for it to be continuous, the number of possibilities has to be infinite. And obviously, if there's an infinite number of possibilities, we can't squeeze them all into a table. So the fact that these are listed in the table is enough to show you that these are discrete, or these would be discrete if they had the right probabilities. So discrete, again, simply means we have a finite number of possible values for X. Although it can be a large number, it just has to be finite. Continuous, which we'll study in the next chapter, can have an infinite number of possible values. Now, typically the way it works out, mostly with discrete random variables, they're restricted to integers, although not always. Like for example, if X represents the number of people who come into a store during a given hour, it has to be discrete because there's only, the number has to be an integer. It can't be infinite, okay? But if X is the time until the next customer walks in the door, that's a very different matter because time can have a fractional component. And because of that, the number of possible times until the next customer walks in the door is literally infinite. So that would be a case of a continuous random variable. Okay. Or here's another simple example. X is the number of students in a class that are left-handed. Well, obviously, this has to be an integer. You can't have 2.3 left-handers. So therefore, X is discrete because it must be finite. Or if it's the time until the next text message arrives. Again, because there's time, time can have a fractional component. It could, for example, be 1.2147 minutes. So the number of possibilities is infinite, and that X would be continuous. All right. So this chapter, once again, is only about discrete distributions, two in particular that we want to study very carefully because they're very, very useful in practice. And keep in mind, unlike some other math classes you may have had, the overriding goal of statistics is to be useful, okay, for real world situations. The point of statistics is to try to explain what's happening in the real world in a very systematic way. Other types of math can be very abstract and have no relationship at all to the real world. You're not getting that here. Okay, this is all about what's useful. And so the distributions we'll be studying have proven to be extremely useful in practice. And that's why we continue to use them. Okay, so we know that a table showing all the possible values of X when X is discrete would therefore be a discrete probability distribution, like the one we saw earlier. It's a probability distribution, but we can also call it a discrete probability distribution because, again, of the finite number of possibilities. And you notice it does have the appropriate properties for being a valid distribution because each probability adds up to 1, and it's also somewhere between 0 and 1. Okay, so this one works. We can then use this to define a set of what are called moments. So if you recall, from chapter 3, we defined several measures. The ones we looked at were measures of central tendency, measures of dispersion, and measures of association. We can do the same exact thing for random variables. The only difference is that the names are different in some cases, and the calculations are all different because they involve probabilities. That was not true with our samples or probabilities. Okay, here we do have to take into account probabilities. Now, we're only going to look at 3 of them in this chapter. There's others, but for the time being, we'll stick with 3. And these 3, and by the way, again, I just want to remind you, when we're dealing with random variables, they're called moments. When we're dealing with samples and populations, they're called measures, but they amount to the same thing. There simply are a single number that represents a single key property of that case. In other words, the expected value or mean is the center of all the possible values of X. And of course, the variance and standard deviation are, as you know from before, variance is a measure of dispersion, as is standard deviation, but the standard deviation is simply the square root of the variance. All right, and you recall from the previous chapters that we need the standard deviation because the variance is measured in squared units, which is extremely inconvenient to say the least. So most of the time, the measure of dispersion, in this case, the moment, that we typically choose is the standard deviation. All right, so let's start with the expected value. Now, this is a technical term. You don't need to know this, but I just wanted you to see that this is often referred to as the first moment. And it is called the expected value. I don't know why, but it represents the same information as the mean or the average of X. Okay, so in that way, it's the same as what we did in chapter 3. But the calculations are different. Okay, we have to take into account those probabilities. So last time I mentioned that you could think of the expected value as a weighted average of all the possible values of X. The weights themselves are the probabilities. Okay, so here's the official formula. The expected value is written as EX. Now, here's the summation operator, of course. So we go through all the possible values of X. We multiply each one by its own probability. We add them up, and we come up with our expected value. So you can see it is a weighted average. The only difference is in the previous chapter, we used W here instead of P, but it is the same thing. Also, I do want to remind you too, when we did this in the previous chapter, we divided by the sum of the weights, but here the sum of the probabilities is 1. So we don't actually have to go through the trouble of dividing by 1. All right, that's another difference between the weighted average formula in chapter 3 and here. In that chapter, we divided by the sum of the weights, but we don't need to do that here because we already know that the sum of these probabilities is just 1. All right, so bringing back our famous example of the dice, this is our probability distribution. We can think of these as the 3 X's and the corresponding probabilities. So based on the formula, you can see what we're doing. We're literally just multiplying each X by its own probability and adding them up. And that brings us a total of 1. Intuitively, that should make sense because if you roll the die twice, on average, you should get 1 even, given that an even and an odd are equally likely to take place. So this should conform with your intuition. All right, and hopefully you can follow along those calculations and do it yourself. If I gave you any probability distribution, you should not have any trouble at all calculating the expected value. The variance is a little bit trickier. But it's really no different than what we did in chapter 3. Okay, the formula is the same, except that you're multiplying each calculation by a probability rather than adding them up and dividing by n, or n minus 1. So the variance is called often the second, it's technically known as the second central moment, but again, you don't have to worry about this. I just threw that in there for your own benefit. And basically what they're trying to capture here is the dispersion. In other words, here you can see the x's are very close to each other. They're all very close to 1. So you would expect to have a very small variance. But if the numbers range from, let's say, minus 100 to positive 100, then the variance would be quite large. So it's trying to capture how close these numbers are to the mean. So I mentioned the formal definition is this, but we're not using this to do our actual calculations. This is a more theoretical definition. Now, sigma, oh, I did mention here too, sigma makes another appearance here. If you notice, we use sigma in the previous chapters to represent a population standard deviation, and sigma squared was a population variance. Look what happened. We've used the same variable again. Why? I don't know why. I guess somebody decided somewhere along the way that it should be clear from the context that we're talking about a random variable here. So it should not confuse you when you see sigma squared being used as a variance for a random variable when it's also used for populations. I guess the other alternative was to find a third alphabet, but they decided not to do that. They decided to stick with the Greek. So it should be clear here, the sigma squared refers to a random variable, not a population. And so here's the formula. And I repeated the one for the population up here so you can see the difference. With the population variance, what you're effectively doing here by dividing by n, it's the same thing as multiplying each term by 1 over n. So that takes the place of this probability. So you can see that this is technically still a weighted average, where the weights are the probabilities. So you're going to go through each x, subtract its mean or expected value, square the difference, and then multiply by the probability of that value of x. All right, so again, using that same example with the dice rolling experiment, we're going to calculate the variance, and it'll be exactly like what you're seeing here. So why don't we go to the next slide and actually do it again. So there's the probability distribution on the top, and a quick reminder here that the expected value is 1. So here's what you're actually doing. Look at all these calculations. What are you doing? In each case, you take your x, subtract the expected value of 1, square the difference, and multiply by that probability. When you're done, you add them up. And as I predicted before, the variance is very, very small. In fact, it's actually smaller than the mean or expected value. And of course, that's because the x's are so close to each other. So we know that this random variable has all values that are very close to the center. In terms of, in a different application, if these were returns to a stock, for example, this would mean that the stock is very stable, the returns are very close to each other, it's not very risky. Now, of course, you know what's coming next, the standard deviation. Whatever this number is, the variance, we know from experience that the corresponding standard deviation is simply the square root of the variance. That never changes. It doesn't matter if we're looking at a sample or a population or a random variable. In every single case, the standard deviation means the square root of the variance. So the square root of 1/2, whatever that is going to be our final result when we calculate the standard deviation. Okay. So there it is. All right. Now we're ready to look at two very important, two widely used discrete probability distributions. These are used in practice because they're so useful. And so I started to mention them last time. The first one is called the binomial distribution, and there's a hint contained in that name. So the bi is the hint. Bi means two, of course. Poisson is named after the inventor. I've forgotten his first name, but his last name was Poisson. He invented this distribution, so the name comes after him. It doesn't tell us. In fact, why don't we just quickly see if he's on? Yeah, there we go. Oh no, there's no mention of the inventor. It's a very useful distribution. And in fact, what we're going to use it for is to represent, oh, here he is, Denis Poisson. There he is. No, Simeon. Oh, Simeon Denis. Well, look at that. He was a baron. Woo-hoo-hoo. So we have a member of the French aristocracy here dabbling in probability theory. I don't know if I'm sure he had a few bucks set aside, but he chose to spend his time analyzing statistics, mechanics, engineering, thermodynamics. Wow. Oh my God. Woo, we're dealing with a heavyweight here. So yes, this is a case where we really should name this distribution after him. But what we are focusing on here is the Poisson distribution, which we'll see in a little while, is meant to explain, among other things, the probability of a given number of events occurring during a given time interval. All right. So in other words, if I wanted to know the probability that during the next hour, 5 people come in the bank to use the ATM machine, I could use the Poisson distribution to figure that out. All right. Anyway, so the binomial is reserved for cases where we have an experiment with only 2 possible outcomes, as the name suggests. For example, if I did a survey of our class and I said, all right, everybody, are you left-handed or right-handed? And just for the moment, let's pretend that nobody is ambidextrous. Let's just say everybody is either left-handed or right-handed. That could be a job for the binomial distribution. I could say, for example, what's the likelihood that out of 13, I think we have 16 now, 16 people, what's the probability that 3 of them are lefties? That would be a job for the binomial distribution because there's only 2 things that can happen, righty or lefty. Okay, or now here, oh, the potato chips. I remember mentioning this to you. I saw this on TV, this whole documentary about how potato chips are made, which is a lot more interesting than it sounds, by the way. It really is. Everything is done with machines. It's insane. Nothing, for all practical purposes, everything is done by machines. Even the quality control is done by the machines. Each chip that comes off that line is defined as either acceptable or unacceptable. There's nothing in between. There's no, it's sort of good, it's okay. It's either yes or no. It's good enough to go into a bag or it's not. So the machine finds out which ones are unacceptable by shining a laser beam of some kind on them. And if the color that it sees isn't right, it throws the chip in the garbage. The rest of them go into the bags that you and I buy in the store. So let's say the factory has some sense of how many chips should be unacceptable. Now they know, obviously every chip can't be perfect. Some of the potatoes may not have been that great in the first place. You know, they can get burned. They can, you know, there's all kinds of things that can go wrong in a production process like this, especially when food's involved. It has to be just right. There's a very limited amount of tolerance we can have for unacceptable products. So let's just say that the machines are working properly if 3 bad chips show up in every 1,000 chips. Let's say that anything more than that, we have to fix the machines. So we want to know, without having to count every single chip, what's the probability of this happening? And for that kind of thing, we can use the binomial distribution because the chips are defined as either acceptable or unacceptable. And you can see easily the usefulness of this in quality control. I mean, every product that comes off the line, either it's good enough or it is not, and it has to be discarded. So you can see this could be very, very helpful in that area of business, which we call quality control. No business can survive without appropriate quality control, because otherwise the products won't be very good quality and people will stop buying it. I mean, the reason why you have confidence, that's what brand names are all about, telling you that you can count on this brand. It has a reputation for quality and you don't have to worry about it. All right. So let's start with a binomial. Now, you know from before, we talked about the idea of a random process. Here, there's a random process taking place. We call these individual repetitions of the process trials. You know, it sounds like a jury trial. No, each time we repeat a process, it's a trial. So in other words, every time we make a new potato chip, that could be defined as a trial. And on each individual trial, in order to use this distribution, it must be true that number one, each trial is independent of the other trials. Now, what does that actually mean in practice? It means that, let's say, for example, if you do get a defective potato chip, it does not affect the likelihood that the next potato chip is also defective. Now, with machinery, that may not be the best example because, you know, if something's going wrong with the machine, then you might get a bunch of defectives in a row. But for the binomial distribution, each trial is considered to be independent of the others. Probably a better example would be flipping a coin. If I flip a coin and it turns up heads, the next flip is not affected by the first flip. I'm just as likely to get a head or a tail on the second flip, no matter what the first flip was. So I could consider each flip of a coin to be independent of the other flips. All right, so in other words, if my experiment consists of flipping a coin and observing whether it turns up heads or tails, each flip is considered to be a trial. The trials are independent of each other. Each trial only has 2 possible outcomes, of course. Now, we use the words success and failure in this distribution, but we can define anything to be success and anything to be a failure. So let's say I could arbitrarily decide that heads is a success and tails is a failure. It makes no difference which I call heads a success or which I call failure, as long as there's just 2 of them. Now, by the way, you might be wondering what happens if there's 3 outcomes. There is an actual probability distribution in that case. It's called the trinomial distribution, meaning that each trial has 3 possibilities. Now, it's much more complicated than this one, so we're not going to use it in this class. But if you find yourself taking a more advanced statistics class, you might run into it. All right, you never know where you might end up in the future. You might find yourself in a graduate program where you have to take more stats classes. And well, all of a sudden, here comes the trinomial distribution. No, not here. It's too much too soon. We'll stick with binomial. And the probability of success, we'll use the Greek letter pi here to represent that. Now, why is that happening? You might wonder why they don't use p. The problem with P is that it's used for a lot of different things in statistics, and we don't want to get it confused with other P's. So in this book, at least, the decision was made to call that pi. Not 3.141 that you know from high school. Pi represents the probability of success on a single trial. And that is assumed to be constant from one trial to the next. That cannot change. If it does, we're no longer dealing with the binomial distribution. And so again, this ties back to our example of the flipping coins. The chances of getting ahead is always 50%, no matter how many times I flip that coin. So an experiment that consists of flipping a coin and observing whether it turns up heads or tails would be a perfect example of this binomial distribution. So under these conditions, we can use a very special formula to calculate probabilities of a given number of events taking place. For example, if I want to know the likelihood of getting 5 heads when I flip the coin 10 times, I can use the binomial probability formula. The only other option I have is to write out all the possibilities and then count them, which could be done, but it gets very, very time consuming. In fact, if I flip the coin 10 times, you'll be shocked to hear that the number of possible outcomes is 1,024. And I don't want to mess around with 1,024 outcomes to figure out the likelihood of getting 5 heads. That could take a very, very long time. Imagine how long it would take to write out that list of all the possible outcomes, all 1,024 of them, and then going through and picking out all the ones that have 5 heads. It could take a very long time. So this is why we prefer to have formulas. Okay. And this is why the random variable is so important, because if we're using heads, H's, and T's, then all we could do is write up a list. Okay. So instead, we get to use this formula. Now, let's see what this formula is about. The formula is a little bit involved. It introduces some concepts that you may not have seen before. But that's okay. We'll do them right now. And when we're done, you'll say, oh, that wasn't so bad. In fact, it was even kind of interesting. So if X was generated from this type of random experiment, then we say that X is a binomial random variable. Okay, like flipping the coin 10 times and observing heads and tails, that X, which represents the number of heads, is a binomial random variable. Now, here the word parameters tells me that there are 2 things that uniquely characterize this random variable: the number of trials and the probability of success. If I know these 2 things, I know everything I need to know about this distribution. In other words, these 2 numbers uniquely characterize this binomial distribution. Okay, or we can just simply say X is binomially distributed. All right. So what I'm going to do now is show you the formula. Now, when you see the formula, don't panic. There's some mysterious parts to it that we'll explain as we go along. All right. So if you're ready, let's take a peek. So now, obviously, you've seen all of this. Pi, of course, is the probability of success on a single trial. N is the number of trials. And then X is the number of, now, oh, by the way, we have to be careful here. You notice I'm using both a capital X and a lowercase x. X is the random variable that we have defined. And lowercase x is the number of successes whose probability we're trying to calculate. Don't worry, this will all make sense when we start doing these. So that leaves one big mystery. What is this thing? By the way, I'm trying very hard in my handwriting to distinguish between the capital X and the lower x. What I'm trying to do is make the x, the lowercase x, a little fancier, so you don't get them confused with each other. The x actually only shows up right here anyway, the capital X. The lowercase x is the one that we really care about. That's the number of successes that we're trying to figure out the probability of. All right, so what we're going to do now is take a little detour into a different branch of mathematics to look at this thing. All right, so the formal definition of this is, now look at this. You may not recognize these symbols. So we're going to define those next. What does that exclamation point mean? Well, it turns out that it is a mathematical operator that you possibly have run into before. If not, we're going to explain it right now. This is, first of all, it's pronounced factorial. Okay, let me show you on the next slide. Factorial. N with that exclamation is called N factorial. Now, what does that actually mean? It means this. 0 factorial equals 1. 1 factorial equals 1. And then after that, it gets interesting. We have 2 factorial, which is equals to 2 times 1. 3 factorial is 3 times 2 times 1, which is 6, of course. 4 factorial is 4 times 3 times 2 times 1, which is 24. And so from that point on, we just keep doing the same thing. In other words, 5 factorial would be 5 times 4 times 3 times 2 times 1. And it just keeps going on and on and on. Now, depending on which calculator you have, you probably have this button built into your calculator. If you're using the Texas Instruments series, let's say you wanted to calculate 8 factorial. What you would have to do is type 8. Then you hit the math function or button. Then you have to shift over to the PRB menu. And when you get to the PRB menu, go down to 4, which is the factorial. And then you hit enter. Wait a minute, hold on, I'm doing it on mine. And then you enter again. And it should come up with 40,320. Now, if you have a different calculator, a lot of those calculators do have this thing on there called X factorial, where you would type, let's say the Texas Instruments Business Analyst 2 Plus, if you have one. And also the iPhone has its own scientific calculator, which if you're using that, by the way, let me just show you. If you're using the iPhone calculator, you know it's high. Oh, wait a minute, what happened there? I hit the wrong button. Okay, you may not have known that if you turn it on its side, it becomes a full-blown scientific calculator. It does have this button built in there somewhere, X factorial, in the bottom left-hand corner. And in a case like that, you would hit 8 and then the X factorial button. And you don't need an equal sign or anything. It just comes up as 40,320. So what is it for? All right, well, this number, now, let me add another slide here. The factorial operator, among other things, can be used to determine the number of ways that n objects can be arranged. Now, what do we mean by that? For example, if, let's say you have 3 books on your shelf where there's only room for 3 books. We'll just call them book A, B, and C. Each of the following is an arrangement. You have ABC, ACB, BAC, BCA, CAB, CBA. Okay, so if you notice, I've got 3 books on a shelf that only holds 3 books. How many different ways can I put those books on my shelf? Well, there they are. There's 6 of them. And the interesting part is that while, yes, you can count them all out, there are 6 ways to place these books on the shelf. Each of these ways is known as an arrangement. The number of arrangements is 3 factorial, which equals 6. It's not a coincidence. Because you have 3 books, the number of arrangements that you can create with them is 3 factorial, which is 6. So by just changing the order of the objects, each different arrangement, they're called arrangements, the number of ways of doing this is n factorial. So if we had 4 books, it would have been 4 factorial. If it was 5 books, it would have been 5 factorial. So it simply tells us how many ways of arranging n objects. So here's another quick example that I put together. What if we're looking at posters? You got room in you've got space in your room for 3 posters from left to right, let's say. You've got one wall in your room. There's just enough space for 3 posters. All right, you got your wall here. And there's stuff on the floor here, but there's room right here for 3 posters. There's just enough space for all 3 of them. All right. This is the stuff on the floor down here. All right. So those are the posters that you own. You have the Yankees, you have Salvador Dali, and of course you have to have a poster about statistics because it's so much fun. How many different ways can I hang these posters? Well, that's the same thing as saying how many ways can I arrange 3 objects? And of course you can make up a list, which I did here. And you see that there are indeed 6 of them. But why go through all that trouble? Now that you know how this works, instead of counting them all like this, you could just say, oh, It's just 3 factorial. Now, let me just quickly show you why this is happening. All right, well, think about it this way. Why are there 6 possible arrangements? Well, the way you have to look at it is when you choose the first poster, you have 3 options. You can choose one of 3 posters. But once you've chosen that one, when you get to the second poster, there's only 2 left. You can pick one of the 2 remaining posters. And then when you get down here, there's only 1 remaining poster. So the number of choices you have could be written as 3 times 2 times 1 is the number of choices or arrangements. 3 for the first poster, 2 of the remaining, there's 2 left, so there's 2 choices for the second poster, and now at the end there's only 1. So that makes it 3 times 2 times 1. Altogether, you have 6 ways of arranging your posters. Okay, now, that was fun as far as it goes, but, by the way, I also put in the instructions here for the TI 8384 series. When you combine, though, these factorials into this equation that you're seeing here, this has a very specific interpretation, though. This isn't just a random jumble of factorials. It means something very specific. This formula represents, now here what we're looking at is the number of ways of choosing X objects from a collection of N objects. Now again, that sounds very abstract, but we'll go through this in a second. And then each of these choices actually, let me just add one more thing here. This is an important detail. The number of ways of choosing X objects from N where the order of selection does not matter. When that happens, each choice is referred to as a combination. So we'll see some examples in a second. It'll start to make sense when you see some examples. All right, so imagine the following situation. I go to Haagen-Dazs and they have a special offer today. Any 3 toppings are available for $1. Okay, pick any 3 and they'll give them to you for $1. Now, these are the ones they have to choose from. We have gummy bears, we have marshmallows. Ooh, doesn't this sound good? Chocolate chips, whipped cream, and Oreos. Now, does the order in which I select my toppings make any difference? It does not. They're all going to get dumped onto the top anyway. So in a case like this, each choice that I have is referred to as a combination. The question is, how many combinations can I create by choosing 3 toppings out of 5? So why don't we do this? Why don't we write them down just for the heck of it? It's not a huge number. Just because, I want you to see how this works. So let's just use the first letter. So you can pick GMC for gummy, marshmallow, chocolate chips. GMW for whipped cream, GMO for Oreos, MCW, MCO, and then finally CWO. There are 6 possible choices when the order does not matter. Now, what do I mean by that? The order does not matter. If you notice, for example, GMC and let's say MGC are not listed separately. You notice there's no MGC in this list. Are not listed separately because they're considered to be the same combination. In other words, if 2 people walked up to the Haagen-Dazs window and said, the first one says, I want gummy bears, marshmallows, chocolate chips. And the second one says, I want marshmallows, gummy bears, and chocolate chips. You couldn't tell them apart. The 2 people who chose the same 3 toppings, you couldn't tell their ice creams apart because they're just all sitting on the top anyway. So these are considered the same. So there's only 6 distinct or unique combinations that we can create when we pick 3 toppings out of 5. Now, that was a lot of work. Should I go through all those steps, or should I use a formula? Well, remember, I mentioned earlier that the formula I'm trying to keep these in the right order. Let's do the formula now. The formula for the number of combinations is N. In fact, let me go copy it back here so you can see it again. There we go. So in our example with the the toppings, N is 5 because we have 5 toppings. And X is 3 toppings are chosen. So in our example, N is 5 and X is 3. So if I copy these into this formula, let's see what happens. Have you noticed I'm using this wonderful equation editor that lets me do this, which is kind of cool. 5 factorial over 3 factorial times 5 minus 3 factorial equals 5 factorial over 3 factorial times 2 factorial. Now that in turn equals 120 over 6 times 2, which is 120 over 12, which is 10. Oh, wait a minute. No, is that right? Did I miss something before? No, hold on a second. Uh-oh, I may have made a mistake here somewhere. Hold on. It is 10. Okay, then I must have, when I made that list, I must have overlooked something because I only got 6. This is the right formula. Oh boy, let's go back and look. Oh, hold on a second. I'm just cleaning this up a little. Yeah, because it doesn't, clearly all that information doesn't fit on one line. All right, let's see if I made a mistake here. I've got 10 here, and yet when I listed them, I must have missed something. Well, let's find out. What could have gone wrong? Let's see, did I miss any? Obviously I did. So let's see what's missing. We have G, MC, GMW, GMO. Oh, I know what I missed. Okay, yeah, I missed a few of them. All right, I see what I did. Okay, I didn't get G. Yeah, I missed GCW and GCO. Did I miss any of the others? Yes, I must have. I missed MWO. And, what else did I miss? No, there's still one missing. I have to figure out what it is. GWO. Okay. There we go. Sorry about that. Yes, I miscounted some of these. Yes, there's 10. All right. So this is why I use the formula instead of trying to count them. Counting them is such a headache that you can see how easy it is to make mistakes. But there's 10. When you use the formula is good. The formula works. All right. This is better. Okay, great. But yes, and again, but this still holds. I mean, you see what I did not do. There's none of them, like here, for example, there's no choice here where it has the same 3 letters as any of the others. So these are not listed separately because they're the same combination. All right, well, now that we got that fiasco straightened out, but the bottom line is that there's 10. All right, you choose 3 out of 5, and there's going to be 10 choices. Even if making the list is a pain, there are 10, as we've proven now. Now, you're probably wondering, now remember I mentioned before, when we define this, the order of selection does not matter. What if the order does matter? Well, that's not really relevant for the binomial distribution, but I still think it's important for you to see this. If the order matters, then the name changes. And I have to change something here. I use these slides for another class, and I had to fix that. If the order of selection matters, then each choice is known as a permutation. And so imagine I've got 20 students in a class who decided to start up a statistics club at Purchase. The club, in order to satisfy the school's rules, must have a president, a vice president, and a treasurer. Otherwise, the school won't approve the club. And nobody wants to take one of those jobs. They're all like, well, that's okay. I don't, everyone's being very modest, and they don't want to step forward and accept one of those jobs. So I have to pick them myself. Now, if I randomly pick 3 out of 20 students, look what happens this time. What if I pick students number 1, 3, and 7? That means student number 1 is the president, student number 3 is the vice president, and student number 7 is the treasurer, because I chose them in that order. But you notice what would have happened. Suppose I picked the same three numbers in a different order. Instead of 137, I picked them as 713. Now they're the same three students, but look what happened. Now it's student number 7 who's the president, student number 1 who's the vice president, and student number 3 is the treasurer. And that clearly is very different than what I had in the first place. So now all of a sudden the order of selection matters. And so each possible selection is referred to as a permutation instead of a combination. So we don't need that for this class. I just wanted, for completeness sake, for you to see that there also exists permutations where the order does matter, and it does have its own separate formula. Now, here's a fun little twist. This is sort of a fun historical side note that I came up with in my travels. The statistician Ronald Fisher was once at a party. Now, Ronald Fisher is one of the big names in the history of statistics. He invented a lot of what we're using in this class. And so, but he was a brilliant guy, and all he thought about was statistics, apparently. He went to a party where it was a tea party. And there was a lady there who claimed, now these people were drinking tea. And apparently, this was in England, I believe. The tea that was being served was what we call a cream tea, which has tea and milk in it. And there's a woman at the party who said, listen, apparently the waiter poured into her cup. I think what ended up happening was there was milk in her cup and he poured the tea in on top of it. And she said, no, don't do that, please. I like it better when the tea is poured first and then the milk. And then the waiter basically said, well, how can you tell the difference? And she apparently said, I can tell the difference. And so what Ronald Fisher said to himself was, let's find out if this is for real or not. I mean, I don't see how, but let's try it. So what he did was he devised an experiment in which he said, all right, here's what we'll do. We'll go into the kitchen and we'll make up 8 cups of tea. Half of them will have the tea poured first, and half of them will have the milk poured first. Okay, so what we're going to do is have the lady taste each one of these without knowing which is which, and she will identify whether the milk came first or the tea. So out of 8 of them, just out of curiosity, how many do you think she got right? Just for the fun of it, who wants to make a guess? How many do you think she got right? Now, I'll tell you what, I just completely forgot about this. I actually have the ability in this class to create what are called polls. So we can have a little fun with this. The title of the poll is Tea Lady. How many did she get right? All right. So it's a multiple choice question. We'll go from 0, 1, 3, 4, 6, and all 8. Now, of course, you have no way of knowing. I just for the fun of it, why don't we just see? This gives me an excuse to use polling. I completely forgot that I have this device at my fingertips. Okay, so if you're reluctant to vote, we'll stop. We'll cut it off at 30 seconds. No, we got some more votes. I'm obviously not voting because I know the answer. All right, well, most of you are correct. It turns out she got all 8 of them right. So this actually illustrates a few different important ideas. Number one, now Fisher, being Fisher, this is his area. He used the binomial distribution to determine that there was only a 0.39% chance of her getting all 8 of them right by pure chance, which means that she really knows the difference. And so for this lady, the T's themselves are permutations because the order matters. For the rest of the guests, they would have been combinations because the order did not matter. So the lady was right. She could tell the difference somehow. I don't know how, but she did. And Ronald Fisher wrote this up as a paper because it was such an interesting outcome. Not the kind of thing you normally run into at a party. All right. A statistical test and a breakthrough in statistical theory. But it happened, this was in the beginning, this is the very beginning of the 20th century. It's still pretty much the Victorian era at that time. So it was very interesting. Anyway, so let's jump ahead a little bit here. What if you want to not use this actual formula, but what if you want to use your calculator? There is a function in there somewhere that will let you do this. And it's on the same menu as the factorial operator. Let's jump ahead here a little bit and look at this next example. A house is being painted. We're going to pick 2 out of 4 colors. All right. Now, presumably, the order in which I pick the colors doesn't make any difference. So how many different combinations of paints can I choose? All right. Well, again, you can write them all down. In fact, I did actually do that. 2 out of 4, they're combinations, so the order doesn't matter. And so by writing them all down, you'll see that the number of possibilities is 6. And if you also notice, I did not separately write white and green because that's the same combination. But these, by the way, are 2 different permutations. So these are all the combinations that we can create. Okay, that doesn't count because it's just the same 2 rearranged differently. But how to do this with your calculator? Or actually, first, let's use the formula. So in this case, we have N is 4 colors to choose from. And X is 2 colors to choose. If you plug these into the formula, you'll see that you have 4 factorial over 2 times 4 minus 2 factorial, or 4 factorial times 2 factorial. Let me just get these in here better. And then what you end up with is 24 over 2 times 2, which is, of course, 6. All right, now, in order to do this on your calculator, at least on the TI-83, 84 series, you start with a 4. Now remember, you're trying to solve for 4. Now, sometimes this is written, by the way, as 4C2, which is pronounced 4 choose 2. The C means it's a combination. So you go to the, you start with the 4, then you go to the math menu, go to the probability menu. Number 3 is NCR. Then you hit 2. NCR means what I just showed you up here. The C is the combinations. 2 is the last value, and then hit enter, and you'll get your 6. All right, I hope you're all trying that out. And so you should get the right answer. All right, so now let's look at another quick example of combinations we can practice on our calculators. Another scenario where the order is irrelevant. We're choosing objects from a larger collection. Suppose that we're playing draw poker. Every player gets 5 cards. Now, the order of your cards does not make any difference. So what's happening here is that each hand of 5 cards chosen from the entire deck of 52 could be defined as a combination, because you're picking 5 objects from 52 where the order does not matter. So how many hands can you create with a standard deck of cards? Well, clearly, you're using the combinatorics, the combinations formula. N is 52, and R, or X, is, we'll call that X. The calculator calls it R. We've been using the letter X. The calculator, remember, calls it R. It doesn't matter. N is the number of objects. The R or X is the number you're choosing. Well, let's plug in the numbers. So what you do, wait a minute, why is there a 4 here? Oh, you know what you have to do? Wait a minute, I think something's wrong here. It should be 52 first. I'm going to do it on my calculator. 52, math, probability, number 3, enter, and then enter your 5, and you get the correct value. Yeah, that's it. Okay, now we're ready then. So in other words, all of this discussion was just to help us understand in the binomial formula what this thing is. Okay, and you can see now nx, this is just the number of ways of choosing x objects from n when the order does not matter. Okay, these others are pretty clear. I mean, the probability of success is raised to the x power. 1 minus the probability of success is raised to the n minus x power. So we're about to start some actual examples here of the binomial distribution. And we're going to do it, you know, the long way, step by step. And then I'm going to show you some shortcuts in the calculator. Okay. But since it's 11:15, you know that it's time for our usual morning break. And so when we get back, be prepared to do a lot of binomial probabilities. Okay. All right. I'll see you all in a bit. All right, it's time for the binomial distribution. So, all right, so we were back to this die rolling experiment. We roll the die twice. So basically, you might remember that we already calculated the probabilities for these this experiment. We have the probability distribution up here somewhere. So basically, we already know how this is going to turn out. But what we're going to do is show that this can also be obtained, these results, by using the binomial distribution. Okay, and so let me just copy this in here somewhere. So we already know what to expect, but let's just see how we can get these same numbers by using the formula. Let's see, where should this go? Okay, so and while we're at it, let me get the full formula and bring it down here. And once we start using the formula, you won't want to go back to charts, that's for sure, because it's so much more straightforward. And of course, especially after I show you the shortcuts on the calculator, that'll really save us a lot of time. All right, let's grab this and sneak it back into these slides. All right, so the idea here is, so first of all, if you recall, we rolled the die twice, which means n is equal to 2. All right. And remember also we defined even as a success. So by calling x the number of evens, even is what we call a success, which means that odds is a failure. So what that tells me is that pi is 0.5, because this is the probability of a success, or in this case, even number. That's only because we chose that to be the case. In other words, it's always true that the pi is a probability of success, but we decided to define success as an even number. And remember, we said that these are the only two numbers you need to uniquely characterize the binomial distribution. Now, the rest is, what numbers are we trying to calculate the probabilities of? So we want to reproduce this entire probability distribution and basically prove that these probabilities are correct. So we'll do all three of these. We'll start with the probability that x equals 0. So first we plug everything in. Remember, n is 2, x is 0, pi is 1/2. So the first thing you want to do is calculate this term. And this, remember, in English can be pronounced 2 choose 0. Because there's 2 that you're choosing from, of which you choose 0. Now, if you go to the formula, the combinations formula, and plug in these numbers, you'll discover that there's only one way to do this. All right, so that value is 1. And in addition to that, so this is 1. We just figured that out. In fact, you know what I'm going to do? Let me copy this on here so you can see it. Which you can do with the formula, or you can go to your calculator and use the NCR function. You can use 2 NCR 0 on your calculator and you'll get 1. 0.5 raised to the 0, any number raised to the 0 power is 1. Okay, you might recall that no matter what x is, when you raise it to the 0 power, it's just equal to 1. So these first two terms are just 1s. And then this last value, 0.5 squared, is 0.25. The product of those three numbers is 0.25. And of course, that's the same thing as 1/4. So we've confirmed that this value is correct. Excellent. All right, so we plugged in all the numbers and we end up with the correct probability of 0.25. So we're proud of ourselves right now that we did this correctly. And now what about x equals 1? What's the probability that x equals 1? We already know that it's a half, but let's prove it with the binomial formula. So let me do one thing here. Remind you what that formula looks like, and also remind you that here n is 2, pi is a half, but here we're trying to figure out the probability that x equals 1. So once again, you plug everything in. And so first you have to deal with this, the number of combinations here, which is on the next slide. I'll copy this up here. And this time it's 2. There are 2 ways of choosing one object from 2. Now each of these, as you can see, is just a half. Remember that x to the first power is just x. So basically what I have here is 2 times 1/2 times 1/2. Which is a half. And that's exactly what it shows on the chart, except the chart says a half, here it's 0.5. It doesn't matter. So it works out pretty well. All right, well, you know what's coming next, the probability that x equals 2. Let's check that out. All right, let's move this down here. And so here, oh wait, sorry, that's the wrong one. That's the same one we just did. Here we go. So now we continue to have n equals 2. This never changes. Pi is 0.5. But in this case, x is 2. So you plug in all the numbers. Now, let me go grab this formula for you. And you can see that once again, this first term is just a 1. 0.5 squared is 0.25. This last one, we raise it to the 0 power, so it's just 1. And voila, we're done. So all 3 of these are, of course, the same as what we had originally when we simply counted up how many even numbers turned up. So here we're using the binomial distribution to show the same results. Now you might say, well, what's the big deal? Who cares which one we use? If you have a lot of trials, then counting them up becomes very awkward. As I said before, if we were to flip the coin 10 times or roll a die 10 times, you don't want to go through a list of that size. So instead, this is when you would want to use the binomial distribution. Okay, why don't we do another one real fast just to get some practice? In fact, this will be your challenge for the morning. Suppose that a game is played in a casino. A wheel contains only 2 colors, red and black. There is a 40% chance of getting red and 60% chance of getting black. Okay, so here's what we're going to do. Now, we're assuming, of course, that the spins are independent of each other. Suppose the wheel is spun twice. Using the binomial distribution, compute the probability. Oh, and one more thing, wait. Define red as a success. Using the binomial distribution, compute the probability of getting 0 reds, 1 red, and 2 reds. So it's very similar to what we just did, except the probabilities are different. Instead of the probability of success being a half, it's only 0.4 this time. So let's, first of all, let's copy this formula. We'll note, oh, what happened? Let me go grab the formula. And the first thing we have to note is that n is 2, but now pi is 0.4. So to calculate the probability that x equals 0, we have, we're 2 out of, this is 2 choose 0, 0.4 to the 0 power. Now this is 1 minus 0.4, so it's 0.6, and n minus x is 2. Okay, so n, actually, I'll note this down here. In this problem, x equals 0, so that n minus x is 2. So now you plug in all these numbers. So now your challenge is to come up with that probability. All right, so let's see how long that takes. I'll give you a minute, and then we'll see what you get. Now, you might recall, this one we've already seen before. The number of ways of choosing 0 objects out of 2 is actually 1. This one, of course, is also 1. So the challenge, 0.6 times 2 raised to the 2nd power. Look how easy that was. .36. All right, then we'll do the same thing for x equals 1. Make sure you got the right answer, by the way. And while we're at it, let me go grab that formula for the combinations, as long as it's here, just so there's no doubt in your mind what just happened. Okay. Now we'll do the same thing for 1. So I'm going to recycle this slide. All right, let's try that again. So for this one, this is part B. I'm just going to make a few quick changes here. X equals 1. All right. I just want to make sure it's set up the same way. So here we're looking for the probability that x equals 1, x is 1. That means that n minus x is 1 as well. Okay, and this formula is now not correct. Let me just quickly fix it. All right, so now go ahead and take a shot at that and see what you come up with. Now, this one I've already given away the game. The first one is just 2. These are raised to the first power, so they're just whatever you see right there. So if you multiply these out, you'll get 0.48. Up here was 36. All right, that just leaves x equals 2. All right, so I'm just going to make a few quick changes. Okay, and of course this one is wrong. And it's not letting me edit it. I'll just fill in the other stuff first. It's being a little stubborn with me right now. Okay, there we go. It's actually letting me do it. Okay. So we have 1 times 0.40 squared times 1, 0.16. So what we should do now probably is make sure that we didn't make any mistakes by creating, let me leave that there for a second, by creating a little table so we can make sure that the rules that we defined earlier are defined, are met here. In other words, it has to be a valid probability distribution. All right, so we'll gather up all the results and put together a little table. So let's see, what did we get here? 0.36, 0.48, 0.16. Do they add up to 1? Let's see. We'll throw them into the calculator. 0.36 plus 0.48 plus 0.16 is 1. So, and of course, each one of them individually is between 0 and 1. So we have ourselves a valid probability distribution, which was generated with the binomial distribution. So that turned out very well. Now, with all that being said, while this is not very difficult, if there was a shortcut, you might be tempted to try it. Well, I'm going to show you a shortcut right now. Let's go back and revisit the dice rolling experiment. Now, the formulas are fine, but it turns out that, especially with this calculator, if you go to the button second, hit the second button and then VARS, you'll see a whole slew of probability distributions that you can choose from. So you scroll down until you find letter A, which at least on the 84, is called Binom PDF. And that basically stands for the binomial, it stands for probability density function, which is a fancy way of saying this is the formula for calculating binomial probabilities. So then you hit the enter button and you'll notice that it's asking you for information. What kind of information? Well, let's see. It needs to know the number of trials. Now remember, this is the die rolling experiment. There were 2 trials. The probability of success of an evens was 0.5. Since you're trying to calculate the probability of getting no evens, X is 0 here. Then you hit, in my case, it says paste enter. And when it comes back to the full screen, you should have 0.25. So how easy was that? Very easy. A lot easier than using the formula and a lot less prone to mistakes. So the calculator has this function built into it. And you might as well take advantage of it. Okay, so there it is. Let's use it. You don't have to. You can double check your results with the actual formulas, but just be aware that this is here. Now, what about X equals 1? What is different? Let's find out. It's just the X value. Okay, so in other words, as far as that's concerned, you just change the value of X to 1, and you've got your answer, which is 1/2, which we know is correct. All right. And what about 2? Well, again, you only have to change the value of X. So when you go back to the menu, you'll notice that all the numbers are still there. The only thing you change is the X. And there you go. So we got all 3 probabilities in no time at all. And with no mistakes. So anyway, now guess what? We're going to go revisit the tea lady example. What's the probability of randomly guessing the correct value of each of the 8 teacups by pure chance when there are 8 teacups? Now we're assuming, remember, we assume that half the cups have milk followed by tea, and half of them have tea followed by milk. So the probability is 0.5. All right, so in other words, if you say, I think it's tea followed by milk, there's a 50% chance that you're right just by pure chance, because half of them are tea followed by milk, half of them are milk followed by tea. There were 8 trials, we had 8 cups. The probability of getting them all right means that X equals 8. So what is the probability that she got them all right by pure luck? So we put in all these numbers, and you'll see that we got, I mentioned that earlier, 0.0039, which is just a fraction of a percent. The chances of getting all 8 of them right by pure luck are so tiny that Ronald Fisher concluded that she clearly knows what she's talking about, because this is what it would take to get all 8 of them right by pure chance. In fact, sometimes it's been done in the past where schools are able to prove that somebody was cheating by using this type of technique, because if somebody consistently was getting answers correctly, well above what they would get by guessing when they clearly didn't study, they can use this information to show, well, wait a minute, something suspicious is happening here. So anyway, but here, so Ronald Fisher did these calculations and came up with to the conclusion that the chances of her getting them all right were so low that she must know what she's talking about. Now, it's still possible. This is one of the ways in which statistics is often different than other disciplines. We deal in terms of probabilities. It's hard to ever make a definitive yes or no statement that she definitely knows or she definitely doesn't. But what we're saying here is that the chances of getting them all right by luck are so low that we conclude that she knows what she's doing. You know, it's like a trial. When you decide, you know, you acquit somebody, let them walk free, you never can be absolutely sure that they're innocent, but you're just saying that there's a very slim chance that they were actually guilty, and not, you know, slim enough that we can let them walk. All right. Now, we mentioned before in this chapter that there are moments that we can define for a random variable. And we've already done that. Remember, let's go back and revisit that for a second. We had 3 that we were focused on, although there are more: expected value, variance, and standard deviation. And we saw the formulas. Here's our expected value. Here's our variance. And of course, the standard deviation is simply the square root of this. And they're not that complicated, but if we had a lot of possible outcomes, it could get very messy in a hurry. Like, let's say we roll a die 20 times. Calculating the variance could be very, very time consuming. Fortunately, as it turns out, as we'll see will be the case with many distributions, there are actually shortcut formulas that we can use to calculate the moments of the binomial distribution. And when you see them, you'll say, wow, those are shortcuts compared to the original formulas. So for example, the expected value means you take the number of trials and multiply by the probability of success. Now, how easy is that? It's easy. It's crazy easy compared to what we had to do before. Even with just 3 outcomes, it took a while to get that number. Here, we're just multiplying 2 numbers together and we're all set. So then the variance formula, which was quite involved, is quite easy as well. It's just, essentially, you're just taking what you had before and multiplying it by 1 minus pi. Look how easy that is compared to what we had to go through earlier. And then, of course, the standard deviation, as you can imagine, is simply the square root of the variance. That never, ever changes. So why don't we do this? Let's go back to the, let's go back to the case of the die rolling experiment and recalculate the expected value, the variance, and the standard deviation. So the expected value, now we can see how easy this is. Remember, it was 1 before, but now we just multiply the number of trials by the probability of success to get that 1. The variance is really easy now. Remember what a pain it was before? 2 times a half times a half, and we got our correct answer. Look at that. Wow. Now that's what you call a shortcut. And it doesn't matter if there's 2 trials or 200. It's the same formula. And of course, the standard deviation is easy because it's just the square root. All right, so the square root of a half is approximately 0.7071. Okay, we're not completely done with the binomial distribution just yet. We're going to use a histogram to illustrate what it actually looks like based on the values of n and pi. So The binomial distribution actually is what you would call a family or a class of distributions. In principle, there can be an infinite number of different binomial distributions. Each one is uniquely characterized by n and pi. In a way, it's kind of like people. You know, if you know their first and last name, not really, because more than one person can have the same first and last name, but more or less, that's what it looks like. In other words, if you know the n and the pi, that uniquely characterizes that particular binomial distribution. So we can see this visually with histograms. So I picked 3 examples. In each case, there's 10 trials. We're going to change the probability of success, or pi. All right, so in other words, I've randomly chosen 3 pi's, 0.2, 0.5, and 0.7. And you'll see that each one of these graphs is unique. It's almost like a fingerprint that uniquely identifies that particular distribution. Okay, so here's 0.2. What do you notice about it? Well, the majority of the values are over here at 2 and 1. In other words, if I conduct a binomial experiment with 10 trials and the probability of success is 0.2, the majority of the time I'll get 2 successes, and I'll get 1 success not quite as many times, followed by 3. So you can see the outcomes typically are very small. What if that changes to 0.5 now? How does it affect our outcomes? Ooh, now look what happened. You can see the bars are pretty much symmetrical about this 5 in the middle. All right, in fact, this one might remind you of the case. You can't really see, there's a tiny little value for 6, 7, 8, 9, and 10. They're not zeros, but they're very close. This should remind you of the positively skewed example we had when the mean was greater than the median. This one looks like the symmetrical case where the mean and the median and the mode were all the same. We have 5 in the middle, and there's a balance between 4 and 6, 3 and 7, 2 and 8, 1 and 9, and 0 and 10. Okay, so this distribution is symmetrical about the center or mean. It's kind of nice. And then when pi jumps up to 0.7, we'll have the opposite of the first case. The majority of the output, or the outcomes, are clustered around 7. And so you can see this should remind you of the case where we had a negatively skewed distribution, because these small values are very unlikely to happen. Most of the results are over here. So just by quickly glancing at these histograms, you can often get a sense of what our distribution looks like. All right, so with all that being said, we're finally done with the binomial distribution. Now we can at least take a peek at the Poisson distribution. Now remember, this is the one that we can use to represent the probability of a given number of events occurring during a time interval. Although it can be used for other things too. Just as a quick example, if you wanted to know the likelihood that, let's say there's X potholes over a given mile of road, you can actually use the Poisson for that too. But here we're going to focus on time. Actually, an interesting example I saw in one of my books was somebody was making chocolate chip cookies. And the question was, what's the probability that 8 out of 10 cookies had at least 2 chips or something like that? And they used the Poisson distribution for that. But here, again, we're going to focus on time. Now, the first thing we need to know with any probability distribution is the probability formula. That is what's going to tell us how to calculate probabilities. So here, the Poisson probability formula is a little bit simpler than for the binomial, but it does have some interesting things that we have to introduce. All right, so I may as well just show it to you. So what's going on here? First of all, this is a new Greek letter. This is the Greek letter lambda. And here it will be interpreted to mean the average number of events per unit of time. For example, it could be that there are 3 rainy days per month. Or it could be that the Dow Jones goes up a certain number of days every month. Things like that all could be used here. Now, this E is a very special constant. It's approximately equal to 2.71828, but it goes on forever, just like pi. It's a non-repeating value number where there's no repetitions among these numbers in the after the decimal point. So this is an irrational number, just like pi. It's a very special constant. You would, if you ever end up taking calculus, you'll see it in that class. The formal definition, where did it come from? But it's very useful in practice, surprisingly enough, considering how messy it is. It's often used in finance to calculate interest rates, which you might run into if you take a finance class. But here we just use it. Now, by the way, your calculator has this in there too. If you're using the Texas Instruments not the BA, the 8384 series, suppose you wanted to know, let's see, where is it hiding in here? There it is. Okay, suppose I wanted to know, for example, the value of E squared. You would type second log 2, enter. And you'd end up with approximately 7.389, let's say. If you're using the iPhone, then let's see, in your iPhone, oh, there it is. The iPhone is a little different. With the iPhone, you would hit the 2 first. There's an E to the X button over sort of in the middle, top middle row. You would hit the 2 first and then E to the X. The interesting thing about calculators is that they're all slightly different. You have to get used to them. And if you don't know these things, well, a test is not the right time to find these things out. Okay, so so in the iPhone, 2 E to the X, on the TI-83, second log 2, enter. This is the E to the X function. So they're basically asking you to do E to the X 2, enter, and you get the same answer. Now, if you notice here, though, it's a negative exponent. So you have to be careful. Most calculators, in fact, why don't we do that one next? Let's just to make sure. E to the minus 2 on the TI 8384, you would put second log, and then the negative sign is directly below the 3. All right, second log. Oh, wait, yes, -2. Wait, I did it wrong on my calculator. Yeah, it's 0.1353. iPhone, a little trickier. Let's see. You would put 2. Then there's this plus minus button that takes the place of the negative key up here. So you'd put 2 negative and then e to the x. With no enter sign, and you'll get 0.1353. All right, and of course you may have another calculator, for example, the BA2 plus, which you may have. This is really a finance calculator, but it still has what we need. You would put it's more similar to the iPhone 2 plus and minus, second log, and there you go. Okay, it's the same any way you look at it. All right, now let's look at a quick example when this would work. Suppose that the number of messages that a person receives on his cell phone averages 1 per hour. So that means that lambda equals 1. What is the probability of receiving 2 messages in the next hour? All right, so the formula, let's go grab it again. Is right here. So remember that here lambda equals 1, x equals 2. So if you plug in the numbers, you've got e to the minus 1, 1 squared over 2 factorial. Now 1 squared, of course, is 1. 2 factorial is 2. So 1 over 2 is just a half. So you've got e to the minus 1 times a half. E to the minus 1, let me write this out separately. Is 0.3678, roughly. Or 7.9, approximately 7.88, I guess is a better way to round it. And so half of that is about 0.18395. Okay, so now it turns out that just like with the binomial distribution, you can do this directly in the calculator. There's a shortcut. So go to the same menu and go to second vars again. And go down the list to Poisson PDF. And what it's going to ask you for is just two things, lambda and x. So you type those in and then paste enter, and you end up with 18394, which is what we got. All right, so I'd like to wrap this up now by showing you two more things. Number one, the moments. There are shortcut formulas for the moments here as well as there was for the binomial distribution, except they're even easier if that's possible. Look how simple they are. The expected value is just lambda, the variance is lambda, the standard deviation is, of course, then the square root of lambda. Okay. So let's do this example again. Now remember, in this case, the average number of messages you get on your cell phone every hour is 1. So the moments, very simply, are 1, 1, and 1. Look at that. How often does that happen? All right. The last thing we want to do here is the graphs. We want to do a histogram for each of the three different Poisson distributions. Remember, there's an infinite number of them. Now, by the way, I didn't mention this with the binomial. Each binomial distribution is characterized by n and pi. The Poisson distribution is uniquely identified by lambda. All we need to know to identify the Poisson distribution is lambda. So I'm going to show you 3 cases. Lambda equals 1, lambda equals 2, and lambda equals 5. And we're going to see how they are different from each other. All right, so here we go. With lambda equals 1. Now, interestingly enough, the probability of getting either x equals 0 or 1 are identical to each other, which does happen sometimes with the Poisson distribution, and then it falls off very, very rapidly. So this is a unique characteristic of the Poisson, the fact that these two are the same. Although it does look very similar to the case of the binomial with a low pi. It's like that, skewed to the right case that we saw in chapter 3. When lambda goes up to 2, the two identical bars move a little bit to the right. Now we're equally likely to get 1 or 2, and then of course it falls off very quickly. And then finally, with 5, the two identical ones are 4 and 5. This one looks a little bit more symmetrical. This is more like the case where the binomial had a pi of 0.5. Okay, so now we could do as many as we want, but that's plenty. You can really see what's going on. So that, as you can see, was it. That's all we really needed to do for the binomial and the Poisson distributions. So we're kind of zooming along here, which we kind of have to, because it is, after all, a 4-week class. And at some point, we have to start thinking about a midterm. Not yet, but soon enough. And then we're going to spend a fair amount of time reviewing for that midterm. Okay, but right now we'll just carry on. Tomorrow, we'll look at the next chapter, which is 7, where we introduce one of the most important distributions in all of statistics, the so-called normal distribution. And we're going to get a lot of mileage out of that because we'll keep seeing it over and over again, not just in this class, but in any other stats classes you might take in the future. So it'll be more complicated because it's a continuous distribution, but it's awfully, awfully important. So anyway, I think we're done for today. So we'll just say goodbye until tomorrow. And unless there's any last minute questions. If not, oh, wait a minute. Sorry, I see 3 chats. Yes, there is. Actually, I think I may have already posted. I'm glad you asked. It won't be due to next week. If it's not there, I will put it up extremely soon, but I think I may have stuck it up there over the weekend. Hold on one second. Good question. I'm pretty sure I may manage to get it in there. Yeah, no, not yet. Okay, no, I'm working on it. I'll take care of that today so you can get started as soon as this afternoon. Yeah, I know that they're fairly time consuming. It won't be due to next week, but yeah, I want you to have it as soon as possible, especially since now that we're done with chapter 6. So I'll take care of that this afternoon. All right. Anything else? Other than that, I guess I'll just see you all tomorrow. Okay. Bye, everyone.